Good morning. I'd like to look at spherical coordinates now, and to avoid any possible confusion of notation, rho is going to be the distance from the origin to the point that I'm interested in. Theta is going to be given by the same equation that we had in polar coordinates in 2 dimensions. Phi is going to be the angle that the line segment that connects the origin to the point of interest makes with the positive z-axis. You can write down equations that tell you the spherical coordinates in terms of rectangular, and just as easy, if I know the spherical coordinates, I can write down the Cartesian coordinates. X, y, and z are regarded as independent variables in our calculations, so rho, theta, and phi will be as well. If you'll remember, a coordinate basis is formed by taking the position and doing the partial derivative of the position with respect to the various variables. So E1 is the partial of position with respect to coordinate number 1. That would be coordinate number rho. If I take the partial derivatives of these three quantities with respect to rho, I get these three quantities. E2 is the partial derivative of x with respect to theta, so I'll treat rho as a constant, phi as a constant, and it's the theta that I'm thinking of as being the variable. The partial of x with respect to theta is easily seen to be this, and partial of x with respect to phi is this. The components of the metric tensor are the dot products of the basis vectors. So if I know how to do Cartesian dot products, which I do, then I can just write down E1 dot E1, E1 dot E2, and E1 dot E3. It's worth mentioning that I already know G21 and G31 now because of the symmetry of the metric. G22 and G23, which is equal to G32, are also easy to calculate. And lastly, G33 works out to be the square of the rho coordinate. We now know the components of the metric in spherical coordinates. Using the horrible G notation for the determinant of that collection of quantities, we find out that G is rho to the 4th power sine squared phi, so that radical G is rho squared sine phi. We're going to need to note some of those combinations of Christoffel symbols, but because of the fact that we talked about in a previous video, these are very easy to get. Here, I'll just take the partial derivative with respect to variable number 1 of natural log square root of g, and then by using the ordinary chain rule, I find out that that's 2 divided by rho. Gamma mu 2 mu is the partial derivative with respect to theta instead, but this quantity doesn't contain any thetas. It has no theta dependence, so that one will be 0. Gamma mu 3 mu is the partial derivative of natural log rho squared sine phi with respect to phi, and after doing the chain rule, that one turns out to be the cotangent of theta. And the last bit that I'll need is I need to know the inverse matrix to the matrix of lower metric tensor components. This is particularly easy though, because the inverse of a diagonal matrix is formed just by taking the reciprocals. of the numbers on the diagonal. Why are we doing any of this? I want to point out something that's related to classical physics now. If u is a scalar function, then the Laplacian of u is the second partial of u with respect to x plus second partial of u with respect to y plus second partial of u with respect to z. Those of you who've had electromagnetism will recall that this is a very important quantity to us. How does it relate to all of this tensor stuff? I can write it in a sum. I can write it using the comma index. I can use the comma index again. If I have a scalar function and I take the partial derivatives of it with respect to the coordinates, I get the components of a one form, which we had previously called d tilde u. So the thing inside these parentheses are components of a tensor of a certain type. Unfortunately, we've also seen that if you have tensor components and you do ordinary partial derivatives of them, the result is usually not components of a tensor. In Cartesian coordinates, all the Christoffel symbols are 0. That means that u upstairs I, downstairs comma I, is the same as u upstairs I, semicolon I, when I'm thinking about Cartesian coordinates. But this is a scalar. This must be a scalar also. This is a tensor equation of type 0, 0, a scalar equation. If it's true in one coordinate system, it's true in all coordinate systems. But I know the definition of the covariant derivatives of vector components. I can just write it like that. And notice, Christoffel symbol, same index upstairs, same index downstairs, and some other index. Those are those special numbers that we talked about when we were talking about the identity in the previous video. We have already figured out that quantity, and that quantity. U with an index upstairs is the same as Gij u j downstairs. The metric tensor is diagonal in spherical coordinates, so each such sum consists only of a single term. That means I can immediately write this. G11 was 1. G22 in the downstairs version was rho squared sine squared phi, so this is G22 of the upstairs version. Likewise here, one of our sum of Christoffel symbols worked out to be 2 divided by rho, one worked out to be 0, and the other one worked out to be 1 over rho squared times cotangent of phi. The punchline of all this is, if I know some coordinates and I know the metric in terms of those coordinates, we were able to write the Laplacian in spherical coordinates by doing a very systematic thing. We looked at the partial derivatives of the vectors with respect to their coordinates. We did some dot products. Out comes the metric tensor. In this case, it was diagonal, so the inverse was easy to get. We used that theorem about the gamma, mu, alpha, mu quantities to just write these terms down. As I mentioned previously, if you've had some electricity and magnetism, you know that Laplacian is important. I've written out the formula for the Laplacian in spherical coordinates again, and I'm going to ask a question that's seemingly out of left field. And yes, that is a terrible joke. I want the Laplacian of u to be 0. This is the Laplace equation. This is the equation that electrostatic potentials and gravitational static potentials have to obey. Also, I want spherical symmetry. I don't want my solution u to depend on theta, and I don't want it to depend on phi. And what I'm hoping to get out of this is sort of a classical result that we all probably know. If u only depends on rho and not theta and phi, then any term that has a partial derivative of u with respect to theta or with respect to phi is 0. The Laplace equation simplifies down to this. If you multiply through by rho squared, you can make the observation that this is equivalent to the derivative. Really, there's only one variable here. The derivative with respect to rho of rho squared derivative of u with respect to rho is 0. That means that rho squared du d rho must be a constant. Du d rho must be constant over rho squared. The only spherically symmetric solutions to the Laplace equation are the inverse distance solutions. When you take the negative of the gradient of such a thing, you get an inverse square field. This is all I'm going to say about this today, but we are getting there now. Coming up soon, what does any of this have to do with gravity? Until then, I hope everyone's taking care during this bad patch of weather that we have here, and I'll talk to you again soon.